We continue with our series of lectures on molecular vibration, molecular spectroscopy. So in the last video we talked about what vibration is, which is oscillatory motion about an equilibrium point, and then we talked about the general selection rule, which is a dynamic dipole, which means as with vibration there must be a change in dipole moment, either in direction or in magnitude. Now let's talk about the vibrational frequency. We can consider a vibration of a mass attached to a wall. So this is mass M attached by a spring to a wall, and it keeps moving up and down. That's an oscillatory motion of vibration. We can look at this mass as its equilibrium position being at x equal to 0. So it goes out as it compresses. As it compresses, there's a force that moves it back to the equilibrium position, and if it goes over the equilibrium position, the force restores it back to the equilibrium position. According to Hooke's law, the force, which is the restoring force that brings it back to the equilibrium position, is directly proportional to the displacement x from the equilibrium position. So x can go either direction. So the proportionality constant with symbol K is called the force constant. We also know that from Newton's second law of motion, that force is equal to mass times acceleration, and the acceleration is related to the displacement by d squared x over dt squared, where t is time. Now this equation ma equals is a linear homogeneous second order equation where the general form for x is given by a cos 2 pi vt b plus b. T is the time, which is the same thing from here, time in second, and this symbol here, B, is the frequency, that is the number of cycles completed in a second, and B is just the phase of vibration, which can always be taken off or set to 0. A is the amplitude of vibration, that's the maximum displacement. So if we compare this equation, if we take this derivative d squared x dt squared and compare this to equation f equals ma and f equals kx squared, involves a little bit of our calculus, we arrive at the v, which happens to appear first here, is equal to 1 over 2 pi the square root of k over m, where m is the mass of the vibrating object. So m is the mass of this vibrating object. So the frequency of vibration is 1 over 2 pi. So it's directly proportional to the force constant, that's the proportionality constant, and inversely proportional to the square root of the mass of the object, vibrating object. Now if we were to take this to molecular spectroscopy, we're considering diatomic molecule first. The frequency of vibration becomes 1 over 2 pi square root of k over mu. Mu in this case replaces m, that's m1, m2 over m1 plus m2, where m1 is mass of one of the vibrating diatomic molecule. The diatomic molecule is made up of 2 atoms. It's called the reduced mass or effective mass, and again this is the frequency of vibration. For molecule, k is usually not called a force constant or rather it is called the bond strength of the molecule. So next we talk about the energy levels that occur in a vibrating system. The simplest approximation that we can use to look at this is called the harmonic oscillator approximation. It's the simplest approximation used to model a diatomic molecule or vibration in general, as the simplest model for vibrational motion. A simple harmonic motion is a periodic motion that is neither driven nor damped, and that means that it just keeps going back and forth. Nothing pushes it and nothing stops it. It's the object in a simple harmonic motion also experiences a net force which obeys the Hooke's law that we talked about in the last slide. Now for our diatomic molecule, our X is now the changing bond distance. So this is our equilibrium bond distance. The changing bond distance, R, can be smaller, that's compression, or longer, that's when you elongate the bond. So there's a periodic motion that goes back and forth between this compressed bond length and this elongated bond length while passing through the equilibrium bond length. The potential energy associated with the vibration V is related to the force by this equation, V dV minus dV dx equals F. And since our F is minus kx, we can simply integrate this to get that V is a half kx squared. So using the half kx squared in our quantum mechanics equation, we arrive at the various energy levels that can be obtained in a vibrating system. So the energy of a vibrating system is equal to V plus half times h, which is our Planck's constant, times the frequency of vibration. Now this V is it's called vibrational quantum number, meaning that our energy is quantized, our vibrational energy levels are quantized. So so this is a picture of a potential energy diagram V against X. So a large K, the potential energy is very narrow, and a small k, the potential energy is big. So let's look at the characteristics of these energy levels. EV is written from the previous slide. So remember again, this is a mathematical derivation from quantum mechanics, which is not the focus of this video. So the energy levels, we can draw it out. Remember, if you plot V against K, you get a curve, a potential energy curve. So if we start with V equal to 0, we have, and put it in there, 0 plus half, we have half h nu, or half hv. So our E0 is half hv. What we note about this is that half hv, the 0, the smallest energy that the molecule can have, is not 0. It's actually a definite value, which is half hv. This quantity, half hv, is called the 0-point energy of the molecule. It is the minimum energy that a molecule can possess, a diatomic molecule can possess. So it depends, so meaning that a diatomic molecule cannot have a 0 energy. It is in constant vibration. It depends on the mass and bond, it depends on the mass present and the strength of the bond, since it depends on the vibrational frequency. So if we put in E1, if we put for V equals to 1, so we have 1 plus half, that's 3 halves. If we put in for V equals to 2, we have 2 plus half, that's 5 halves, 5/2. So our energy levels keeps going. What we notice is that as you go higher, the spacing is the same regardless of whether you are in the high region or in the low region. If we recall, for rotational energy levels, which is characterized by the quantum number J, as you go higher, the energy spacing keeps on increasing. Okay, so the energy spacing here, they are all equal to h nu. We can easily put that in calculation in an equation. So the difference between an energy level EV and the one next to it on the high side, simply by substituting V plus 1 into that equation minus V plus half. So you arrive at HV, which is the spacing between all the energy levels. From the harmonic, the specific selection rule for V is that V can only change by plus or minus 1. Remember, the specific selection rule is the selection rule for the quantum number that characterizes the energy level. So here, the V can only change by plus or minus 1. It's convention to label the V equals to 0 to V equals to 1 the fundamental transition or the fundamental band, and then the V to 1, V to 2 or higher ones are called the hot bands. So this is like a summary of what we've been talking about. The lowest energy level is the 0 point energy, and it has a value of half HP. Then we have the next one 3 halves HP, the next one 5 half HP, and the separation between subsequent energy levels is HV. The allowed transitions, V can only change by plus or minus 1. So if your molecule is in 5, it can go to 6 or go to 4. From 0 to 2 is not allowed, so it's called a forbidden transition. And if you recall, once such transitions occur, it's not going to be intense. So hot bands, any other transition other than the fundamental transition. So in the next video, we will consider an harmonic approximation.